All right, welcome to another episode of Science with Surbeck. Today we're going to focus on the isotope review, and to go along with that, we'll talk about atomic mass. So what I want you to be able to do by the end of this video is the first objective, be able to define an isotope and use the standard notations used to note an isotope. The second objective is to be able to define what atomic mass is. And then that third and final objective is to be able to calculate the actual atomic mass from an example problem. So let's get started here and talk about what isotopes are. So isotopes are defined as atoms with the same number of protons but different numbers of neutrons. And so just as a reminder, remember the atom. We'll draw a real simple model of the atom, but inside the center here, these pluses and N's, that's the nucleus of the atom, and those things that have an N by it are my neutrons, and those things that have a plus sign by it are my protons. Now, surrounding the outside of the nucleus, you have all of these electrons, and I'm going to draw them in an orbit. That's not the best way I can represent it or model it, but for our purposes here, the electrons would be on the outside of that particular atom. Now, one thing to note with our isotopes is that these isotopes, just because they have different number of neutrons does not define their chemical behavior. The chemical behavior is actually given by the number of protons in the nucleus. And that's something we'll emphasize later here in notes. So an example that we have of an isotope is the potassium isotope. So potassium is element number 19, and that means it has 19 protons. And so one thing to note is this: every single potassium isotope has 19 protons. What is different in each and every isotope of potassium is the number of neutrons. So one example or one isotope of potassium is potassium 39, which contains 20 neutrons. A second isotope of potassium, potassium 40, contains 21 neutrons. And then that third isotope of potassium, potassium 41, contains 22 neutrons. So the other thing that we need to have in mind when we talk about isotopes is how they occur in nature. So the relative abundances of each isotope is constant, but is not the same. So if we go back to our potassium example, potassium 39, in nature, there is 93.25% abundance of all potassiums are potassium 39 isotopes. Again, if we had all the potassiums in the entire universe, 92.25% would be potassium 39. Now, potassium 40 has 6.7302% abundance in the universe. And then potassium 41 has a very, very small percent abundance at 0.0117% abundance. So again, these are the percent abundances of each of these isotopes. Now, what we can shift gears to is mass number. So, our mass number is defined as the sum of protons and neutrons in the nucleus. And so it's important to note here that the mass number does not determine the chemical behavior of an atom or an element. This mass number, this chemical behavior is caused or determined by the number of electrons an atom has. And again, that is the number sign for number of electrons. Now, what's really nice about the mass number is that it has a formula. And that formula is the mass number is equal to the number of protons plus the number of neutrons. Again, mass number is equal to the number of protons plus the number of neutrons. Now, what we can do, we already alluded to some isotope notation on the previous page, but I want to talk about the two types of isotope notation that we have. The first is the element name notation. And so in this notation, the element name form is going to write the name of the element followed by the mass number. So an example of this would be that potassium 39 element or isotope, where again we wrote the entire name of the element from the periodic table. So we wrote out potassium, and then we put a dash, and after the dash we put the mass number. So I told you this was potassium 39, so 39 represents the mass number. Now the other way that we can write this is the element symbol form. And so in this notation here with the element symbol form, it is going to write the element symbol with the mass number on the top left and the atomic number on the bottom left of the symbol. So again, if we're sticking with that same example of potassium 39, how we would write it in this element symbol form is we would first look up the symbol of potassium, which if you take your periodic table that I've given you and you find potassium, what you do is you write the symbol. So the symbol for potassium is just a capital K. And make sure you leave a little room, because on the top left you put the mass number, which if we're dealing with potassium 39, 39 is the mass number. And on the bottom left, you put the atomic number, which remember the atomic number is that whole number on top or above the element symbol. So for potassium, the atomic number is 19, and that's how we would write that. So what I want to do before we leave talking about the mass number, I want to go over an actual example of this business here. So what we have here is an example, and so we are given the isotope of neon 22. We want to know what the number of protons, electrons, and neutrons are in this isotope. So what we do first is we start out and we have neon 22, and I'm going to rewrite this down below, and we are going to talk about it. So neon 22, what that dash 22 means, if you look back on your periodic or your previous page of notes, this right here is the atomic number. Oh, I'm sorry. This right here is the atomic mass. Made a mistake there. That's the atomic mass. What we can do now is we can plug this into our formula. So what we're going to do, what formula that we use for this is the atomic mass is equal to the number of protons plus the number of neutrons. So what we're going to do, we're just going to plug some number in. So again, that dash 22, I made a mistake there. That should be the atomic mass like I have written here now. So for neon, the 22 becomes our atomic mass. And if you wanted to be particular, that would be 22 AMU, or atomic mass units. And then we can set this equal to the number of protons. Well, notice here how the problem never says anything about protons. and that's because it's right here on the periodic table. So for neon, if you find neon, which is right here, Ne is the symbol, and above it is this whole number, which is the atomic number, and that number is equal to the number of protons. So our number of protons equal this top number of 10. So that right here is our number of protons. So if we have 10 plus our number of neutrons, we now have a really simple problem to be able to solve for the number of neutrons. All we need to do, think like algebra, to get rid of 10, we just subtract 10 on each side. 22 minus 10 is 12, as the number of neutrons for neon 22. We said that 10 was the number of protons, which is equal to that atomic number. So 10 equals the number of protons, and then the number of electrons, which from previous notes I said in our atoms, until I tell you otherwise, they're going to be considered neutral. So if they're considered neutral, the number of protons has to equal the number of electrons. So that means because we have 10 protons, that becomes the number of electrons that we have to have. Now, before we leave this page, I want to write neon 22 in that symbol notation. So how we do this is, again, we look for the symbol, which if you can't remember, neon symbol is right here. It is Ne, so we start out by writing Ne. In the upper left-hand corner, we write the atomic mass, which for this isotope is 22. And then in the bottom right-hand corner, we write the atomic number, which is equal to that number of protons. So this would be 10. And that's how we would write that element symbol notation. Okay, one more major thing that we have to do for these notes, and that is to talk about the atomic mass and go over a brief calculation for how that atomic mass is found. So the first thing that I want you to do, mass number, or think in your mind, mass number is different than the atomic mass. So the atomic mass, by definition, is just defined as the weighted average mass of the isotopes of that element. And this atomic mass is not normally a whole number. And so the other thing that I want you to keep in mind is that the atomic mass is based on the atomic mass unit, which we've talked about in AMU. And I'm not going to write this down, but an atomic mass unit is just defined as 1/12 the mass of a carbon-12 atom. Again, that's their baseline for how they get atomic mass unit. Not so important for us here in the review. What we need to know is that, hey, atomic mass is the weighted average mass. Again, it is different than the mass number that we just calculated. So we have an example here, and that is of chlorine. So chlorine naturally exists as a mixture of about 75% chlorine 35 and about 25% chlorine 37. So again, there are two forms for chlorine. The first of those forms is chlorine 35, and there is about 75% abundance for chlorine 35. And the other form of chlorine that naturally is existing in a mixture is chlorine 37, which has about 25% abundance. So taking this into account, when we do our atomic mass calculations, we have to take the business of the isotope atomic, mass number and the percent abundance. So what happens with chlorine is that gets combined in a mathematical way, which I'm going to show you. And so that means that because more chlorine-35 exists, the atomic mass, if you read it out on the periodic table, becomes 35.453. And again, that atomic mass, when you see that on the periodic table, is in the units of AMU, or atomic mass units. So what I want you to be able to do is we calculated mass number. Now I want you to see how atomic mass is calculated. So to calculate this business here, what you need to do to calculate that atomic mass is you need to identify the atomic mass and percent abundance of each isotope. And I put in parentheses here that this is given. So you will never have to come up with these numbers. It's either going to be given to you in a word problem or in a chart. The second step is to multiply the atomic mass and percent abundance of each isotope. Once you have done that for each and every isotope, you are going to add all of the values together that have been calculated in that previous step or in step 2. And then the fourth step is to write the atomic mass with the correct unit, and we're going to round to 2 decimal places in this class. Okay, so we're going to try a quick example, and then we will be good to go for notes for this section. So I'm going to transfer the pages, and we're going to get this example. So we are given the data in this table below, and we want to calculate the atomic mass of this unknown element X and identify what it is. So again, those percent abundances and the atomic mass of each and every element will be given to you. So it'll be given to you in a chart or in a word type of format in a question. So what we need to do, step 1, is to take your atomic mass and multiply it by its abundance. So what I'm going to do for this isotope X6 is I am going to take the mass exactly how it is written here, and I'm going to take 6.015 AMU times the percent abundance. Now, this right here is a percent abundance. So what you need to do for anything that is in a percent, what you do here is you take 7.5 and whatever that number is, you divide it by 100, and so that becomes your decimal form. You need to make sure that this is in your decimal form. So 7.5% becomes the decimal of 0.075. Now what you do, because you have the percent into a decimal form, is you take 6.015 and you multiply it by 0.075 and you press enter. Now on this, we can go out to 4 decimals is fine for us, but that is 0.4511. And the units again would be AMU. Now, we have to do this for every isotope that is present for any particular element. So we move down to this X7. We're going to do a very similar thing where we need to take the atomic mass, which is 7.016, AMUs for atomic mass units, and we need to multiply it by the percent abundance, but we must take that out of percent form and put it into decimal form. So again, we have 92.5%. So in our calculators, we have 92.5 divided by 100, and so that gets us a decimal of 0.925. And so that is what we're going to multiply this by. And I'm going to put that into my calculator and get a number once more. So once again, I'm just going to put 7.016 times 0.925. And I'm going to press enter. And I can go out to 4 digits once again. So I get 6.4898. And that unit, again, is AMU. Now, for us, what we are going to do here is we are going to add these numbers together. So all I'm going to do is I'm going to take this 0.4511 plus 6.4898, and that becomes my atomic mass of the element that I'm trying to identify. So again, I just take in 0.4511 plus 6.4898. And when I press enter, I get a value of 6.9409. And I told you in the previous slide that you can round to 2 decimal places. That's going to be our standard when we talk about atomic mass. So right here, this becomes the value of this becomes 6.94 AMU. Now we're not quite done. That's one of the answers. It said, hey, what element is this? So what we need to do is we need to find an element with an atomic mass of 6.94. So it's going to be relatively small, so it'll be towards the top. And if you look closely, look right here, 6.94. That element is lithium with the symbol Li. So the atomic mass that we just calculated is for lithium. And so the element for this particular answer would be lithium. All right, so this is the final page for this set of notes. What I want you to do, I want you to be very careful. I want you to review what is the mass number versus the atomic mass. They sound familiar, they may even look familiar, but atomic mass, remember, has those decimals. Mass number is going to be whole numbers. Keep that in mind as you go through this review. All right, I hope you've enjoyed this video, and as always, subscribe.